let's talk about other integration strategies. In this chapter, we've been focusing on different ways to integrate different types of integrands. So we've looked at integration by parts, we've looked at trig integrals, we've looked at trig substitution, and we've studied the method of partial fraction decomposition. Now, these are just 4 techniques among many, many techniques, but they're the primary 4. Now, what about all these other techniques? Now, there are hundreds, in fact, over 1,000, well over 1,000, probably around 1,700 by now, known ways to integrate different types of integrands. So we obviously can't learn all of them. That would be ridiculous. So what do? Instead, we learn the main techniques, which are the 4 we've already covered: the integration by parts, the trig integrals, the trig substitution, and the partial fraction decomposition. And then for the rest of the integrals for which there is a known pattern, a known antiderivative, we use what's called an integral table or a computer algebra system in order to integrate these others. Now, this is a very important skill for you to have, not necessarily in the math class, but for sure in any applied field. So if you're in physics, or you're in any kind of engineering, or you're in biomedical science, you need to actually get an answer for some of these integrals. So you're not so concerned in those particular situations with the process of the integration. You need the result of the integration. And that's what's ideal for using integral tables in computer algebra systems. Now, computer algebra systems are abbreviated CAS, and they're called CASs, which sounds kind of crazy, but that's what they are. So what we're going to focus on in this relatively short section is how to use an integral table, what an integral table looks like. And then we'll talk briefly about some computer algebra systems, and I'll show you some of my favorites so that you can kind of see where they are and what they can do for you. Now, in my classroom, at least, since I teach mathematics and I am concerned with the process, I won't allow my students to use the integral tables on this particular chapter because I want you to know how to do integration by parts, trig integrals, trig substitution, and partial fraction decomposition. I am interested in the process. So I'll only allow you to use an integral table on a particular problem where I tell you basically which integral to use or which type to use. So let me go ahead and share my screen with you, and we'll get started talking about what these different integral tables can look like and how we can use them to find the antiderivative of integrals for which the antiderivative is known. Now, I've said a couple times for which the antiderivative is known. And I've also said there's 1,500, 1,700 known types of integration formulas, which must mean that there's a whole lot we don't know. And we'll talk briefly about this in the next video when we talk about numerical integration. In fact, most functions don't have known antiderivatives. Or we may know it has an antiderivative, but we can't write it down using the elementary functions. So we'll be talking about that in the next video and how we deal with these functions for whom we don't have a known antiderivative. But first, let's focus on using the tables. So the integral tables are just a collection of known patterns that can be used to integrate certain types of integrals. There's a book called the CRC tables, used to be and probably still is one of the most prized books in all of undergraduate mathematics because it has a compendium of all the known patterns at that time. So nowadays you can probably find it online, but there was a time when this book was literally over $1,000, and this was probably 3 decades ago. You can imagine a $1,000 book 3 decades ago would have been, well, I don't know what it would have been today, but a lot of money. Very important. Again, we can also use what's called a computer algebra system. We'll use a couple of online ones, but there are some graphing calculators that have computer algebra system ability. That would be the TI-89 and the TI-Inspire CAS. There's one by Sharp as well, but I can't remember the name of it. So there are some graphing calculators that are capable of this. Now, I've taken the integral tables from Stewart's calculus textbook, since it's a pretty standard text in the field, and you can find these integral tables everywhere out there on the internet. They're not proprietary material, they're known to everyone. Now, in the particular reference list I'm going to use, there's about 120. Now, like I said, there's really more like 1,500, 1,700. I've lost track. There's a lot. We're only going to deal with just a small subset of what is known, because we can only focus on a small group at a time. If I gave you everything, it would be overwhelming, and it'd be like trying to find a needle in a haystack, or rather a needle in a field of haystacks, and it would be difficult to do. When you're doing one of these problems where you're using an formula from the integral table, you will almost certainly need to do U substitution of some kind. So you're going to have to replace the integrand, and you're also going to have to replace the differential. Now, we saw this kind of replacement of the differential when we were doing trig integrals, and also when we were doing trig substitution. So we've seen this pattern of having to substitute out for the integrand and substitute out for the differential before. Now, I will tell you that this is actually as much art as it is science. So there is an art to doing these. And that means that it is very difficult sometimes to find the appropriate choice of U. So what we typically do is we start in the main part, or the primary part of the integrand. So if there's a radical present in the integrand, we would start under the radical and temporarily ignore any factors on the outside of the radical. If there's something in parentheses raised to a power, we would probably start inside the parentheses and ignore any factors that are outside of it, hoping that they will get worked out when we replace the differential. So the key to doing these is really picking the correct U. It is a process somewhat of trial and error. The more you do, the better at it you get. Why? Because you're building up a subconscious understanding of how these work. And so the more you do, the more your subconscious says, hey, I've seen this before, try this one first. So really, when we say that you develop an intuition, what we're really talking about is your subconscious recognizing patterns it's seen before. The only way for that to happen, unfortunately, is to do quite a few of them. One other thing that you might keep in mind is that occasionally, if you have a fractional power on x, sometimes substituting u equal x to the 1 over n is a good choice. Then you can say that x is u to the n, and then you can take the derivative of both sides, and you can use the power rule, right? So when we're looking at this, this is one thing to keep in mind. Now, I've gone through, or I will go through, 3 examples here of how to work with an integral table. So the first thing I want to do is I want to actually show you what it looks like on an integral table. So here is an image of an integral table, part of an integral table, and you'll see up here in blue that it says forms involving the radical of a squared plus u squared, where a is strictly positive. Now, it is important to keep note that that a is positive is important, right? So when it has a squared, we don't know if a is positive or negative. It's telling us to assume that a is positive. So these are radicals that basically somewhere in the integrand have the square root of the quantity a squared plus u squared. And you can see right here, we've got 21 through 27. There's actually a few more at the bottom off the screen. And you can see inside the integrand in each one of these, there is a square root of a squared plus u squared. But the integrands themselves are different. This first one is just the square root of a squared plus u squared. The second one has a u squared factor on the outside. The third one is divided by a u factor. The fourth one is divided by a u squared factor. The fifth one has 1 over the square root of a squared plus u squared, and so forth. So even though they all have this radical of a squared plus u squared, the integrands themselves are different. And that means that when you integrate it, the antiderivative will, of course, be different. What you get on the right-hand side is the known antiderivative for that pattern up to the constant of integration. So u has to replace whatever you used on the left to make your integral fit this pattern. So the key is to pick the appropriate u and u squared and a squared, and then apply the pattern on the right, which is the known antiderivative, using the u and a that you came up with to fit your particular integral. Let's take a look at example 1 and see how this might work. In example 1, we are looking here at the integral of x cubed times the radical of 1 plus 2x squared. So when I'm looking at this, one of the things I noticed first is that I had an x squared under the radical. Now notice again, I focused first on the square root. I am temporarily, not forever, but temporarily ignoring the x cubed. I'm hoping that when I come up with the correct u and I find something to replace the differential dx, that it will partially account for this x cubed that's on the outside. So what I'm looking at here is a constant plus a constant times x squared. When I look through different ones, there are different patterns that I can see. Here's one pattern that might fit. It's got the square root of 2au minus u squared, a greater than 0. Now, why might I pick this one up? Because I see the radical and I see the u squared. However, this one will not apply. This pattern right here in blue does not fit the pattern up here under the radical. Why not? Well, this has a u squared where u is a function dependent on x, but it also, in the other term, has a u present. In other words, if this has x in it, this has x in it. And in my particular integral, my first term is a constant 1. It does not have an x in it. So the forms that look like this cannot be used to integrate the particular integral that I have. And that means I can ignore them. Let's now take a look at the next set. Let me copy this down, and we'll take this across. I've recopied the integral here so that we can compare the integral to the overarching form types. Now let's look at the next two forms that we have down here. We'll have an entire set of integrals in the integral table that will involve some kind of square root of u squared minus a squared, where a is greater than 0. This may look a little bit closer because, again, knowing that u depends on x, it's got x in one term but not in the other, which does match the pattern that I see up here. The problem with this particular pattern compared to this one is in my pattern, I've got a constant plus something with the variable x in it. Well, that doesn't make any sense because this one has subtraction. And that means that this pattern cannot be made to fit this. We're looking for something that is close, that we can force to fit. And again, I can let u squared be 2x squared, then u would be the square root of 2 times x. But I can't fix the fact that this is plus 1 and not minus 1. So this pattern and all of the integrals under this set are not good choices for integrating this pattern that we see here. Now let's look at the next pattern that's down here. In this pattern, what it's done is it's reversed the order of the a squared minus u squared. Remember that u depends upon x. It's a function of x. And so this is a constant thing squared minus a variable thing squared. But again, I don't have any subtraction here, so that one won't work either. Now let's see what else I might find that might possibly work. Here's another example. Let me see if I can paste this down below as well. Here is my example that I've got. This is the integral I'm trying to find. This one looks like we might have a winner. I've got forms of a squared plus u squared under the square root a greater than 0. Well, sure enough, I've got a 1, which could correspond to the a squared, so that a would be 1. Remember, a is strictly positive. I've got a plus 2x squared, which I could let be u squared, so that u would be square root of 2x. So it looks like this pattern might well work. So once we figure that we have a form that might work, then we start looking at the particular ones and see if we can get it to fit the pattern. So we start by selecting u. Now, we're not going to worry just yet about which integral in that particular section we're going to be using. Remember, you have the form at the top and then a list of all the ones that fit that form. So we're not going to be looking through the list yet. We need to try to get this particular integral to fit this particular pattern a little bit. So we know what a is, we know what u is, we know what a squared is, we know what u squared is. So the first thing we're going to do is we're going to try to make the radical part fit the a squared plus u squared under square root pattern. That means that a squared is 1 and 2x squared is u squared. This means that a is strictly positive 1, since a is strictly positive, and u is the square root of 2 times x, or x square root of 2. That also means that I can solve for x. If I can solve for x by using this equation right here, which is relating u to x, then I get x equals u divided by the square root of 2. Now, my original integral not only has the radical, but it also has this x cubed on the outside and the differential dx. I'm going to have to replace each piece with something equivalent to it, but written in terms of u, not in terms of x. So I'm going to need to replace the x cubed, the radical itself, and the dx. By solving for x, I can replace the x cubed by cubing that, which would give me u cubed over 2 squared root of 2. And I can also replace the differential dx. Now, how do I replace the differential dx? I take the derivative of both sides of the equation with respect to u. So let me write that out, because a lot of students get a little bit confused on that particular step. So we're taking the derivative with respect to u of x and the derivative with respect to u of u over the square root of 2. Now on the left side, we have to use implicit differentiation from calculus 1. X does not match the differential, so we get dx du. On the right side, however, the variable is u, which does match the differential, and this 1 over square root of 2 is a constant, and the derivative of u with respect to u is the number 1. So we get 1 over the square root of 2. Then we can abuse the notation. This is the genius of Gottfried Leibniz's notation. We abuse the notation and we swing the differential du around to the right side. This gives us an expression for the differential dx in terms of the differential du. So now we'll be able to replace the dx with something involving du instead. We'll also be able to replace the x cubed, and we'll be able to replace the 1 plus 2x squared using our values for a and u. Now we want to substitute everything that we found so far. So we had the x cubed, which gets replaced with x over the square root of 2 quantity cubed, which is u cubed over 2 square roots of 2. Don't say x, I meant u over the square root of 2 quantity cubed. And then our square root of 1 plus 2x squared becomes that form that we originally identified. It becomes the square root of a squared plus u squared, where a is 1 and u squared is that 2x squared that we see right here. Then we replace the differential dx with du over the square root of 2. Now we do a little bit of algebra arithmetic, and we multiply radical 2 times radical 2 to get 2, and 2 times 2 is 4. So 1/4 is a constant that we can bring to the front. And this gives me u cubed, the square root of a squared plus u squared du. So I've taken my original, I've made substitutions for a and u, and I've replaced every factor inside and outside the square root, and I've replaced the differential. And I've rewritten the whole thing now in terms of a and u. Now I go to the integral tables, and I try to find one that fits that pattern right there. So the 1/4 being a constant is not going to affect the value of the antiderivative of the integrand. It's just a constant. So really what I'm looking for is the integral of u cubed times the radical of a squared plus u squared. This is the particular pattern I'm looking for. So I look under the list of ones that have radical a squared plus u squared for something that has u cubed times the radical. Now, hopefully you can read these coming down here. I'll go through them sort of one at a time. This just has the radical, so that's not it. This is close in that it has the radical times u squared, but ours was u cubed. And you cannot fit a cube into a square, right? Round pegs, square holes, or square pegs, round holes. Won't go. So it's close, but no cigar. This one is not right. It's got a fraction with 1 over u. This is 1 over u squared. That's not right. This one has the radical in the denominator. So does that. So does that. Those aren't correct. Keep going and see if you can come up with one that fits the pattern. And we can't. We've found a representation for the original integral in terms of a and u using the form square root of a squared plus u squared, but none of the ones listed under that form fit our pattern. Did we do something wrong? No, we didn't do anything wrong. We did everything correctly. It's just not a pattern that's listed in this particular integral table. Some other integral table, maybe it is, but how many of these can you check? So what to do? Well, start over. Unfortunately, there's a lot of trial and error, intuition, and instinct that goes into these. And again, instinct, there's no such thing as being born totally gifted at math. I mean, that's a pretty rare thing. What it really means is your subconscious speaking to you and saying, hey, I've seen this pattern before, try this. All right, so we have to develop that instinct by looking at lots of these. Since none of these fit, we're going to have to start over again. This is common, totally normal. Don't freak out. So since that didn't work, let's make a different choice of u. Last time we let u be 2x squared, or u squared be 2x squared. This time, let's let the u just be x squared and see if we can get a pattern to fit. Again, we're starting under the radical, and we're starting with the term that has the variable x in it. That's the part we hone in on first. That's our primary target, picking the right u in terms of x. Last time I let u squared be 2x squared. This time I'm going to make a substitution that u to the first is x squared. Aha, now this is different. Now remember, last time, so let me make note of this so you can compare and contrast the two strategies. U squared was equal to 2x squared. So u is equal to radical 2 times x. This time, though, I'm letting u to the first be x squared. Okay, well, if that's the case, then I could solve for x if I wanted to, and x would become the square root of u, right? I can also take the derivative with respect to u of both sides, and that will give me du is equal to 2x dx. So then I can solve this for the differential dx, which gives me du divided by 2x. So now we have something that looks a little bit different. What does this one look like? Well, I made the substitution that u was x squared, not including the 2. So this looks like a constant plus a constant times u to the first, not u squared. So a constant plus a constant times u, or 1 plus 2u under the square root. Let's go back to the integral tables and see if we can find a form that looks like a constant plus a constant times u. Looking at the integral tables, you'll see that there's a form right here which involves what's called a plus bu. A and b are constants in this particular integral table, which is fairly standard. And u, of course, is some function that depends on x. So a is 1 and b is 2. Well, all right, if I let that be the case, then starting back with my original integral and making my substitutions where a is 1 and b is 2, and u was x squared, and dx is du over 2x, and x is the square root of u, then if I come down here, I can replace each piece. So x here is equal to the square root of u, or you can write it as u to the 1/2. Now, when I'm looking at that and I'm replacing each piece, x cubed becomes u to the 3/2 power. 1 plus 2x squared, where x squared is u, becomes 1 plus 2u. The differential dx becomes du over 2x. But I know what x is. Remember, x is the square root of u, or u to the 1/2 power. So I can replace the x with the 1/2 power. And then u to the 3/2 divided by u to the 1/2. Remember, when the bases are the same, we subtract the powers. 3/2 minus 1/2 gives us u to the first. So I have 1/2 u square root of 1 plus 2u du. So I've written the original integral in terms of x, in terms of a and u. And I've come over here to what I've got now. So what I want to do now is I want to pull up all the integrals under the form of a plus bu and see if one of them looks like this pattern right here. So let's go to the integral tables and let's pull that up and see what we've got. So we've got 1/2 u plus 2u. So let me write the integral up here. U integral. Was it plus or minus? I can't remember. 1 plus 2u du. This is what our converted integral looks like right here when we went from something in terms of x with a differential dx to something in terms of u and possibly a and b and the differential du. So now we start hunting. Now, obviously, one of the main things we need to find is something that has a radical in it, because that wasn't in the form. The form itself was just a plus bu, which is the part under the radical. So we need to find one that has a radical on it. So when we start looking down here, I'm not seeing any, not seeing any. However, this is a super long section. So let's keep looking. Aha, 54. I do have a radical. All right, so the first thing I'm honing in on is this radical of a plus bu. That's the first thing I need to find. So 54 is a possibility here. That looks like it might be one. I do have a radical in 55 and 56, but it's in the denominator, which that doesn't quite match my pattern. Let's go back up and see what the pattern was again. Oh yeah, it's u radical a plus bu. And the 1/2, of course, is just a constant at the front, not going to affect the antiderivative. So really, 54 is looking pretty good to me right now. 55 and 56, I don't think. 57 does have the radical, but it's in the denominator. That doesn't fit my pattern. Keep going. Oh, yes, there are more. Here are the last 5 or 6 that we've got. I've got a radical of a plus bu. That looks good, but it's divided by u, not multiplied by u. So probably 58's no. 59, no, for a similar reason. 60 looks good, except it's u to the n. Now, could I use 60? I think I could use 60, but I would choose n to be 1. So 60 looks like it is a possibility here. I would use 60, but I would choose n equal to 1. 61 and 62 have the radical in the denominator. So it looks to me like it's either 54 or 60, with 54 more exactly fitting the pattern I have, u to the first. Here is the pattern for 54. Now let's go back through and see how we make this pattern fit. So we found a pattern that fits on the left side, and now we have to use the antiderivative formula, the pattern on the right, and make it fit our particular substitution expressions. So we started with the integral of x cubed radical 1 plus 2x squared. We made a substitution here that u was equal to x squared, that a was equal to 1, and b was equal to 2. This also meant that x was equal to the square root of u, and we also had that dx was equal to du divided by 2x. That came from implicit differentiation on u equal x squared, right? Again, I'm using the notation swinging it around to the right. So we have du dx equal to 2x, then swing the dx around and solve for dx in terms of du and x. So we've got this du over 2x, and using the definition of x, we can write this as du over 2 square root of u, or u to the 1/2, whichever floats your boat. Okay, so we've got these substitution equations here, and we're going to take this pattern on the left, and we're going to replace each factor, each piece inside the integrand and the differential with something in terms of u, a, and b. So x cubed becomes u to the 3/2. Dx becomes du over 2x, or du over 2u to the 1/2, square root of u. Our 1 plus 2x squared becomes 1 plus 2u. Simplifying u to the 3/2 or your u to the 1/2, we get u to the first with a 1/2. Pull the 1/2 out, brought us to u square root of 1 plus 2u du. This was the pattern that we were trying to find when we were looking in the integral tables. So this is the one we have. We have got the pattern now on the left. Compare the pattern on the left to what you see up here on the left in 54. A is 1, B is 2. Now take what is on the right side and use that to find the solution to your particular integral. So the pattern that we have is going to be 1/2. Oh, I've got it all off the screen. We can't see it. Let me scroll back a little bit. So I've got 1/2 from the outside of the integral. And then the pattern is 2 over 15b squared. So 2 over 15, b was 2, so 2 squared. Then 3 times b times u, 3 times 2 times u. Now we're going to have to back substitute in a minute with u equal to x squared, because again, if you start with an integral in terms of x, your answer should be in terms of x, minus 2 times a, and a was 1, 1 plus 2u, that's a plus bu to the 3/2 plus a constant. So we get this expression here. Now, this 2 can cancel that 2. 2 squared is 4 times 15 gives me 1/60. And then 3 times 2u is 6u minus 2. 1 plus 2u to the 3/2 plus c. And then the last thing I need to do is I need to substitute out that u is x squared to get my antiderivative in terms of x. So the integral of x cubed square root of 1 plus 2x squared dx is 1/60. 6x squared minus 2 times the quantity 1 plus 2x squared to the 3/2 power plus a constant of integration. And this is how we can take an integral and use the integral tables and the patterns we find there in order to integrate it. Now, it does take time and it takes a lot of persistence. So don't give up when your first effort does not work. There also may be other choices of u that might work. For example, you could try u equal to 2x squared plus 1. In other words, everything under the radical. Maybe that'll work. There's a lot of trial and error here and a lot of using the intuition you've built up from what you've tried before to guide you. Let's take a look at another example. The previous one is quite difficult. This one is not quite as difficult as the previous one, I don't think, personally. We're going to use the integral table, which is given here, in order to evaluate this one here. Now, what's the first thing that makes this one easier? I'm telling you which formula to use. That makes it a lot easier, right? When you don't have to go to the integral table and find it yourself, it's a whole lot easier. So I'm telling you this is the pattern, and it does fit the pattern. I would never give you one that didn't fit. That would be cruel, right? So it does fit this pattern. Your job is to make it fit. So what you want to do is look at the pattern on the left and look at the integral you're given and come up with a definition for what a is and a squared is, u is and u squared is. And then hope that the differential dx helps account for this u squared you have in the denominator, which typically it does. Again, we're focusing on the primary or most important part of the integrand, which is the square root, the radical itself. Why most important part? Has a big effect on what the function looks like, right? And how it operates. So we're focusing on that radical first. Now, when we're looking at these, if I have the square root of a squared minus u squared, looking at what I have under the radical here, I have a constant minus something. And this is a constant minus something. So that seems to fit. I'm not going to worry about what's in the denominator until I figure out what a and u are. A squared looks like it's 25, so that would make a be 5. So that seems pretty straightforward. And that is a good place to start. Now, that also means that the minus is a part of the formula, not a part of u squared, right? You have a subtraction here and subtraction here. That's in the formula. So that must mean u squared is e to the 2x. So if u squared is e to the 2x, which we can see right here in the notes, then that must mean that u is equal to e to the x. Now you may be going, how did she come up with that? Well, remember that if you want to take the square root, it's the 1/2 power, and e to the 2x to the 1/2, the 2's cancel, and you get e to the x. In other words, e to the 2x is e to the x squared, right? So e to the x squared equals e to the 2x, right? It doesn't give you e to the x squared. No. One base, two powers, multiply the powers, all right? So you get e to the 2x. Okay, well then that seems to indicate that u is e to the x, which means that this is a u. Well, now that's a bit of a problem because that doesn't match my pattern. I've got a squared minus u squared over u with a differential dx. But I haven't replaced the dx. This has du and this has dx, and I've got to have du. I have to replace every single piece. So let's deal with the fact that the denominator is not u squared, which is what we were expecting. Are we going to fix this? Well, there's a couple ways of doing it, but one way to fix it is to multiply by 1 in the form of e to the x divided by e to the x. So what I did was I took the original integral here and I multiplied by 1 in the form of e to the x over e to the x. Now I can take the denominator e to the x and slide it under the first fraction to get e to the 2x, and that will leave me with e to the x dx. But remember that e to the x is my u, so this becomes the integral of a squared minus u squared over u squared times u dx. Now, That is not the pattern that I originally had. So let me see if I can scroll back up to the pattern. I've got the a squared minus u squared over u squared, but I need du. And what I have is u dx. So I need to replace the u dx with something in terms of du. So to do that, I need to replace the dx. Since u is e to the x, then the derivative of u with respect to x is du dx, which is equal to e to the x again. Remember, we love exponentials. Their derivative is themselves, their antiderivative is themselves. You gotta love e to the x. So you get du equals e to the x dx. All right. Well, if du is equal to e to the x dx, then dx is du over e to the x. So up here where I have u dx, this becomes du over e to the x. But e to the x is u. So I have u du over u, and the u's cancel, so I get du. Now I have exactly what I was trying to find. I have exactly the pattern that is on the left. So notice how the differential combined with the factors outside the radical fixed the problem of the original denominator not being u squared, but being u. And so I end up with this pattern that I see right here, which means I'm ready to go ahead and apply the pattern on the right side of the formula to get the answer. Here's the formula again, along with the substitution expressions that we've come up with. A squared is 25, a is 5, u squared is e to the 2x, u is e to the x. And we've replaced each piece, so we're ready to use the pattern on the right with these substitution expressions to come up with an antiderivative for this integral in terms of x. So rewriting, I come up with this formula right here. I replace a squared with 25, replace u squared with e to the 2x, replace u with e to the x, and replace a with 5. And this becomes the antiderivative of that original integral, but in terms of x. Now we have one more example that we're going to work. This is example 3. So a little bit more difficult here. This one I don't have worked out ahead of time for you. This one we're going to work out together as we go through it. And you'll see that it is, again, less challenging than the first problem in that I've told you what the formula is, and then I'm asking you to apply the pattern to this particular integral. Now, why would I do this? Well, it's very difficult on an exam to test this kind of knowledge because I'd have to give you the integral tables, and then, I mean, you could spend a lot of time spinning your wheels, right? And not finding the right one, whereas given enough time, you would find it. So a better way of testing is to test whether or not you can apply the pattern. That, after all, is the key. So assuming you can find the right one, can you apply the pattern? And I found that this is actually quite difficult. So we're going to take this pattern here and try to make each piece over here fit the pattern. Now we have a dx over x times the quantity x to the 10th plus 1. Now, what would I hone in on first? Which piece would I attack first? Not the differential and not the x factor by itself. I would hone in on the part inside parentheses. So that would be my x to the 10th plus 1. Now, some students might be tempted to multiply this out. Don't go there. That makes your life so much more miserable. There's a reason it's written that way. So focus on the part in parentheses and see if you can get that to fit this pattern that's over here. So how could we get that to fit the pattern? Well, first off, A has to be a constant, and B has to be a constant, and U has to depend on X. It doesn't have to be X, it just has to depend on X, have an X in it. So I've got a constant plus a constant times something with X in it. Okay, I'm going to start in the parentheses, looking over here, starting in the parentheses. I have x to the 10th plus 1. 1 is the constant term. So I believe that A should be 1. Then I believe that U should be x to the 10th. And that would leave B to be equal to 1. So I'm taking my integral of dx over x times x to the 10th plus 1, and I'm rewriting it in the order 1 plus 1 times x to the 10th. All right, so I'm making it fit the pattern that I see up here, a plus bu, 1 plus 1 times something with x. And I think this will work. So I've got 3 expressions right here for substitution. Now you're looking at these and going, yeah, but you've got other pieces too. Yes, I do. Now it's time to tackle those other pieces. I have an x to the first on the outside of the parentheses and a differential dx. If u is x to the 10th, to solve for x, I would take the 10th root of both sides. So that must mean, coming from that information, that x is equal to u to the 1/10th power, or you can write it as the 10th root. Now that gives me something to replace the x with. What about the dx? The easiest thing to do is to start back with the u equal x to the 10th and take the derivative of both sides with respect to x. So let's do that over here to the side. The derivative with respect to x of u and the derivative with respect to x of x to the 10th. That gives me du dx. Remember, that's implicit differentiation. The u variable does not match the differential dx, and so I'm stuck with du dx. But on the right side, the variable is x, and it does match the differential dx. So I just apply the power rule, which gives me 10x to the 9th. Now, remember, I'm trying to replace the differential dx, so I need to solve this for dx. So I'm going to swing the dx around to the right-hand side. And then I'm going to solve for dx by dividing both sides by 10x to the 9th. Okay, so far, so good. Now the next thing I want to do is I want to take the pieces that I have found. So here's a substitution expression, here's a substitution equation, and the others that are blocked up here in black. And I want to replace each piece in what I have right now to rewrite it in terms of u, so I can apply this pattern that we see up here. So let me write this in a different color. So now I have the integral. dx I'm going to put out to the side. So I'm going to basically have 1 over. What is x? So I'm replacing the x, which is the monomial factor on the outside of the parentheses, which is u to the 1/10. So I have u to the 1/10. That replaces the monomial x. And then inside parentheses, I have a is 1, b is 1, and u is x to the 10th. So this becomes a plus bu inside parentheses. Again, I'm trying to exactly match the pattern on the left. I'm trying to get the integrand to be 1 over u times quantity a plus bu with a differential du. So far, I've got this expression here. Now I need to replace the dx, which I found down here. And so the dx is equal to du divided by 10x to the 9th. Now I have a bit of an issue because x to the 9th is not in terms of u. So I need to get this written in terms of u. But I know that x is u to the 1/10. So I'm going to make another substitution here. So I have the integral 1 over u to the 1/10 a plus bu du over 10 times u to the 1/10 to the 9th. All right, I'm running out of room a little bit. Let me scroll up. Okay, I made a substitution for x. It's still being raised to the 9th power. X was u to the 1/10. One base, two powers, multiply the powers together. So again, I'm doing this in multiple steps, whereas if I were doing it just for myself, I would probably skip steps here and there and combine them. So I have du over 10, u to the 9 over 10, right? I'm still trying to match the pattern on the left. I don't have it exactly yet, so I can't pick up the pattern on the right. So it's got to be precisely, exactly identical to what's on the left before I can apply the pattern on the right. It doesn't look like it yet. Now, the 1/10 is a constant which can come to the front. And then I've got u to the 1/10 and u to the 9/10. They're multiplied. Bases are the same. So I add the powers. 1/10 plus 9/10 gives me u. So the next expression I have is 1/10, the integral of du over u, a plus bu. Does that match the pattern on the left side of the formula from the integral table? Yes, it matches exactly with a constant factor of 1/10 on it. Now I can apply the formula on the right, which is 1 over a natural log of u over a plus bu, which I think I'm going to run out of room. So I've got 1/10. I need to squish it up a little bit so we can see it all at one time. So let me make it a little smaller. So this gives me 1/10. Now applying the formula that's on the right-hand side to this, I'm going to have 1 over a, and I found that a right here was 1. So 1 over 1, natural log, absolute value. What was u? U was x to the 10th. Now what was a plus bu? A was 1, b was 1, and u was x to the 10th. Close parentheses, plus a constant. And we can rewrite this answer as 1/10, the natural log of the quantity x to the 10th over 1 plus x to the 10th plus a constant. Now, I will tell you that there is algebra that you can do here to rewrite this in a slightly different form. You could add 0 in the numerator, add 1 and subtract 1, and then you would get 1 plus something else, and you could, there's a lot you could do, all right? But this is a good form to leave it in. It's relatively clear what the antiderivative is. It's relatively simple. I would just leave it like this. It looks pretty good. But I want you to keep in mind that if you use a computer algebra system and it looks slightly different, that probably what they've done is just apply some of the rules of algebra for dealing with natural logs, or they've manipulated this fraction a bit to deal with it in that form. So that's the end of that particular expression, or that particular problem. So now what I want to do is I want to just take a minute and talk about what some computer algebra systems are and what some of my favorite ones are. So I've got the links to them right here. I'm going to leave it on the screen long enough that those of you who don't have a copy of my lecture notes can actually write these down so that you know them. I wouldn't be surprised if you didn't already know them. These are my 3 go-tos. To be honest with you, my absolute hands down favorite is the first one, and I'll show you why I like that one so much. And then the second one is also super good, becomes even more important in Calculus 3, Symbol Lab does, because it handles multiple integrals. And then the last one is, well, I'm sorry, but it's my last choice. I love Mathematica and Wolfram Alpha, but it's just not as elegant as the first 2. So let me go through and show you now why I like these so particularly much. So if you do have my lecture notes, you can control click on each of these. It is a hot link and it will take you to the appropriate page. Let's look at the first one, which is at www.integral-calculator.com. And we'll talk about why this is my favorite. So This is the page it opens up on. It is a free resource on the internet. It is one of my favorites. It handles both definite integrals and indefinite integrals. You do have to be very good at order of operations in order to type this in here so that the integrand looks the way you want it to look. The default differential is dx, but there is a way to change that, and I'll show you how to do that. So you enter it right here with the caret symbol being powers and SQRT being square roots. You can also raise it to the 1/2 power. Just make sure to put parentheses around the 1/2. The nice part is it does give you an instant image of what it is that you're looking at right here. So let's take a look at the last example that we did, which was example 3, which was the integral of 1/x, x to the 10th plus 1. So in order to enter that, remember that everything is in the denominator. So I'm going to have 1 divided by open parentheses x times more, oops, I got a 9 instead of parentheses, 9x more parentheses, x, use the caret for the power, to the 10th plus 1, close the factor, close the denominator. So that becomes my integral. And you can see right here, it does look correct. Now the default differential is dx. If you have something different, you can always click on it and it will open over here. So it's got all the letters of the alphabet to choose from right here. And if you want a definite integral, you can click on one of these and it will go from upper bound to lower bound and also allow you to choose positive or negative infinity. It also has a way for you to decide whether you want to integrate numerically only, which we'll actually talk about a little bit in the next video, which is on numerical integration. And that basically means there may be no known antiderivatives, so we're just approximating the answer. Simplify expressions, simplify all roots. Again, I don't want you to simplify so that the square root of x squared becomes x. That's not correct. The square root of x squared is the absolute value of x, so don't ever click that box, all right? So basically, I never use these on the bottom. I do use the definite integrals. Most of the time, I just integrate with respect to x, even if it's written in terms of a different variable. Remember, the variable is immaterial. So what do you do after you get it typed in correctly and it looks correct? Click go. Now, why do I like this particular one so much? And you can see that it's working. The reason I like this one so much is that it will first, if it can, simplify your integrand. And this is what it looks like. And if it has been rewritten, it's because you could have done some simplification. What I like about this is that it gives you both a manual calculation of what the integral should be and an antiderivative computed by a computer algebra system. So like a calculator or a computer. This one is called Maxima. Notice that they look slightly different. These answers are equivalent, even though they look slightly different. And notice that this looks slightly different than what I had on my sheet, even though it's equivalent. Now, what I really like is on this manual integration, it has a box that says show steps. And this is what I think is the most effective for students who are struggling with integration, because it will go through and it will apply some different steps, and you can follow through step by step and see what they did. It even has the option right here. It says expand by x, so 1 over x to the 11th. If you don't want it to apply that trick, you can say don't apply this trick and try to get it closer to the one I did. And it will show you what each individual one does. So if I say don't apply this trick, it's going to go back through and it's going to recalculate it using something different. This time it factored the denominator, which it did partial fraction decomposition. So there's more than one way to proceed here. So again, if you want to reset all chosen alternatives, you can reset right here and it'll go back through and calculate. All right. And then it gives you the final result down here at the bottom. Okay. So this is my go-to. This is my favorite one. It's not as effective in Calculus 3 because it doesn't have double integrals and triple integrals, but it's super effective in Calculus 1 and Calculus 2. Now, my second favorite is Symbol Lab. And when you go to www.symbollab.com and you go out into the calculus section, which you click on calculus right here, and then you can click on integrals on the left drop-down menu, and you'll see there indefinite, definite, specific method, improper, antiderivatives, double integrals, triple integrals, multiple integrals. These last three down here are for Calculus 3. So when you get to this one, you can also do the same thing. You type in here, it does have some template boxes at the top. Now, why do I not prefer Symbol Lab? It looks like it's more, well, it looks like it has more options, right? Like it would do more. And in fact, it does do more. But the problem is it's not free. And I'm too cheap to pay for it. So when you do this, it will only give you a part of the solution. And it will give you the solution, but a part of the steps. So one of the things I might start with is parentheses. So I might start with something that looks like 1 divided by x times x to the, again, I used the caret, which popped it up, x to the 10th, use the cursor to go to the right to get out of the power, and then 1 over x times x to the 10th plus 1. And then again, we click on go. And it's going to work. And sometimes it will give you the full steps, and sometimes it does not. Most of the time it does not. This little log symbol says if you want to see the missing steps, you have to pay for more. I'm not a big fan of paying. I'm a big fan of open educational resources. So it does part of it, but not all of it. And you'll see that this particular one, they're using partial fractions. Now, what does that mean? Well, that's the technique that led to the formula that's in the integral table. That's where it comes from. But what we're going to be doing in this section is just using the integral table. So this is my second most favorite, and you'll see that it's got the solution down here at the bottom. And then looking at the last possible choice, this is the Wolfram Alpha option. It also has some templates down here. It is more advanced than it used to be, which is good. You can see that it does have some double and triple integrals. If you're going, I don't know what those are, you're not supposed to know yet because that's Calculus 3, but it's basically 2 integrals or 3 integrals in a row. All right, so they're done from the inside out. And then you have the ability to do definite integrals as well. So you'll see that right here and the indefinite integral here. So you can type in whatever your expression is, and then you can hit return or enter on the computer keyboard, and it should give you the solution. So those are the 3 that I use the most often when I am using something just to get the solution. I just want to check my answer. Then I will use probably the integral calculator first. And if I don't like what I get there, I may go to Symbol Lab and see if they solved it a different way, something that gives me a different idea. In the math class, remember, most of the time we're interested in the process by which you came up with the answer. So we want to see all those missing steps. So we don't want you using the computer algebra system to come up with the answer without going through the process of solving it step by step. So in a math class, expect to not be allowed to use the computer algebra systems to solve the integrals. On the other hand, if you're in physics or you're in engineering, the point of that class is not to solve the integral, but to use the results of the integral to solve some physics or engineering problem. So in a class like that, you will be allowed to use the computer algebra systems to solve the integrals without going through the process of solving each one step by step. I hope this helped you to understand how to use integral tables and to familiarize you with what computer algebra systems are. In the next video, we'll take a look at what happens when there is no known antiderivative. And this will be a brief look at numerical integration. In my class, we solve numerical integration with Python programs. which should make sense to you since we're approximating definite integrals. It makes sense to allow a computer to do those calculations, since the computer can do far more calculations far faster and more accurately than I can by hand. I hope you'll join me in that video.